Hi, good morning everybody. I'm actually now at Microsoft Research and moved on from the university. And I'm going to talk about a simple coordination mechanism for interdomain routing. And my motivation for presenting this work here is because I want to get some feedback from this community whether or not such a coordination mechanism is useful and whether or not these pains I'm going to talk about are actually existing or I made them up. So the nature of the internet routing today is that ISPs work in a contractual framework, and contracts, for instance, would specify that you should advertise for a particular route across all peering links and be willing to accept traffic for particular destinations across all peering links. What happens within such a contractual framework is that ISPs select paths that are best for themselves. For instance, in this simple example with two ISPs and three interconnections and traffic going there from the blue dot to the brown dot, the blue ISP would pick an interconnection that is closest. So this is hot potato routing. It's an example of an ISP selecting path that is best for itself. Similarly, the orange ISP selects this path, and this is the nature of the routing that would emerge in this particular example. Now, such a routing framework has its potential downsides. One is like that ISPs have little control over the incoming traffic. As a result, if you wanted to operate a congestion-free network, you require a much higher bandwidth provisioning. Since you don't have control over how traffic might enter your network, you have to provision for a lot of worst cases if you wanted to operate a congestion-free network. At the same time, because of this greedy path selection that goes on at each ISP along the path, you might see paths that are very long, or you might get utilization hotspots. And there's no automated way today to fix that I know of. So that requires manual tweaking to fix such egregiously bad problems that might arise. Not very common, but they may arise sometimes. And in general, the paths would be somewhat inefficient because ISPs, every ISP along the way is making a greedy path selection, like 3 or 4 ISPs in general. So these are the potential downsides of the nature of internet routing today. So what I'm going to talk about is an alternative approach that I'm going to call coordinated routing. In coordinated routing, ISPs have joint control over path selection. Both the receivers of the traffic and senders of the traffic have some say in what paths get selected. So an example of coordinated routing here would be this, that the blue ISP and the orange ISP have joint control and they decide on a path that is shorter than the greedy path selection or the hot potato routing I talked about. And similarly, this path can result in the opposite direction. And what might be the benefits of such an approach? They follow from the potential downsides of the approach that is taken today. Lower bandwidth provisioning, again, because now you have some control of how traffic enters your network and not only how it leaves. So you have a mechanism that I'm going to describe later, but you have a way using which you can influence how traffic enters your network, and you can steer the traffic away from parts of the network that are likely to get loaded. There would be no egregious cases that would require manual tuning because all ISPs have control. Each of them can fix the path by themselves, and the end-to-end paths would be more efficient as a result. And this can also form the basis of interdomain quality of service, as you'll see, we'll describe later. So assuming we actually want coordinated routing because of all its upsides, can we do that using mechanisms today? On this slide I'll talk about 2 common mechanisms and say why they are insufficient to implement the kind of coordinated routing I'm talking about. One is route optimization boxes, the kind you might get from Internap or Route Science, which would sit at a stub ISP and pick an outgoing path. Route optimization boxes are actually solving a different problem. They are enabling stub ISPs to pick better routes among those available. They are not creating better options in the network itself. So you've got 3 or 4 options depending on the number of providers or uplinks you have, and the route optimization box will let you pick. What it's not doing is it's not finding better paths in the network, such as those in the middle interconnection in that example. Another mechanism is MEDS. MEDS actually implement cold potato routing instead of hot potato routing and do not provide joint control itself. And so here's an example that's on the left. I've shown routing that emerges without MEDS. With MEDS, what would happen? The orange ISP would specify preferences in routing messages, and what results is this particular path over here. Again, what you're getting now is a path that is best for the receiving ISP, and you're not getting joint control. And if both ISPs were using MEDS in this particular example, the routing you get is just the opposite of hot potato routing, and you're not getting the middle interconnection, which offers better paths in the network. So suppose we wanted to invent something different or implement something different. Let's talk about like what would actually be a good coordination mechanism if you wanted to implement it. In my opinion, MEDs in reality, they have some really nice properties that you want in a coordination mechanism. One is that using MEDs, ISPs can express their own metrics. That is, ISPs or network operators don't have to use some globally specified metric, latency, length, utilization, whatnot, to express what their preferences in the network are. So it lets ISPs express metrics that they care about. At the same time, MEDs do not require ISPs to disclose information that they consider sensitive. So as part of playing with MEDs, ISPs are not required to say, well, a MED of 100 means a latency of 10 milliseconds or some such thing. If that information is sensitive, it stays sensitive because you're advertising just one opaque number. MEDs are really lightweight to implement and to use. And they only require pairwise contracts. Only neighboring ISPs have contracts in terms of using MEDs, and this is a really important property in this decentralized internet. Any sort of global coordination proves hard, even when it comes to things like routing registries. There's been problems with that too. Another property that MEDs do not provide, but we would like in such a coordination mechanism, is that the coordination mechanism actually provides joint control, and it benefits all ISPs. And the motivation for that is like unless we give ISPs a coordination mechanism using which all of them can benefit, they're unlikely to use it. So in this slide, I'm going to describe the coordination mechanism. I call it WISER. And to start off, I'll describe WISER in the context of two ISPs, and then I'll show how it works in the general case of more ISPs. Consider this simple example, again two ISPs, 3 interconnections. And those numbers there are, let's say, internal costs that ISPs infer using whatever their network is, whatever properties they care about. Let's say these are cost metrics for carrying traffic from the interconnection to the source to destination. And I'm going to talk about a flow going from the source S to a destination D. So actually how WISER works, it operates in the well-known lowest cost routing framework, not very different from BGP, for instance. So the destination ISP or the receiving ISP advertises its costs. So again, these are kind of like MEDs, opaque numbers that Blue ISP cannot interpret in terms of how they were derived. And what the Blue ISP does, or the sending ISP does, it selects paths based on both the cost it receives and its internal cost. So it's not like routing today, where it takes into account only its own cost. It's not like routing with MEDs, where it takes into account only the receiver's cost. It's actually combining the cost of its own cost and the cost of the orange ISP to pick the path. But sure, I mean, this is not, but there are problems. So what I've described so far is just like lowest cost routing. But lowest cost routing, or the plain vanilla lowest cost routing in the internet, has its problems when you try and apply it globally. First of all, I said ISPs are deriving their metrics or their cost independently. So what that means is ISP cost could be in very different ranges, the way MEDs are today. Some ISPs could be assigning their cost within the range 1000 to 2000, and other ISP might be using 1 to 100. In which case, once you bring incomparable costs together in a simple routing framework, the ISP that assigns higher cost ranges actually wins out. Suppose you were minimizing the sum of the cost or some simple thing. So ISP cost being incomparable and them assigning cost independently is actually a problem. The other problem is the system can be easily gamed. Again, since the costs are incomparable, you can game the system by just assigning your cost that benefits you more, and we lose the property of both joint control and mutually beneficial routing. So in the next two slides, I'll quickly describe how I solve those problems and then move on to how WISER works in the general case. So the first mechanism that throw in on top of lowest cost routing is cost normalization, and the problem here is easy to see. Suppose these are the same numbers that were there on the example, and this is the routing that would emerge if the Blue ISP was taking its own cost and the Orange ISP's cost into account. What the Orange ISP can do is just inflates its cost by a factor of 10, and there's no way to prevent that because cost assignment, remember, is independent, in which case this particular routing would emerge. And now what has happened is routing is a lot more favorable to the Orange ISP, so system can be gamed, and the Blue ISP is forced to implement cold potato routing. The solution to this is what I call cost normalization, which means that I would normalize the costs such that both ISPs have an equal say. That's the intuition behind it. And one potential way to do that is to normalize them such that the sum of the cost that Blue ISP announces to the Orange one and the Orange ISP announces to the Blue one be the same. So after I apply such normalization to the cost that Orange ISP is assigning, 10, 30, and 110 become 0.72 and 7.3. What has happened as a result, the cost of the blue ISP and the orange ISP have now become comparable, and they can be compared directly, and this particular routing would emerge, and we are back to this case. What cost normalization does, it makes the system harder to game, and it also, but at the same time, retaining flexibility. Orange ISP can assign whatever cost it wants, and it can assign whatever relative cost it wants to assign to its links, but it bringing some sort of parity so that ISPs, even if they assign completely incomparable costs, their cost metrics can be compared. This is a property that MEDs don't have today, and it actually becomes very useful when I talk about multi-ISP internet. The other problem with the lowest cost routing is nothing in so far I've said is actually going to stop the senders from not listening to receivers' cost at all. So in this particular example, the blue ISP can keep sending the traffic across the bottom link, which is the best for itself. And the solution to this particular problem also happens to be very simple. I'm simply going to say that the downstream ISP log what paths are being used. And based on those logs, they can compute the ratio of average cost so the downstream ISP in this case is the orange ISP. So based on the logs, they can compute the ratio of the average cost of the paths that are used and average cost of the paths that are announced. And what I'm going to propose then is that you contractually stipulate a bound on the ratio of the paths that we use. And the motivation for that bound is the following. So these are the ratios for those two particular interconnections. Basically, the ratio is a lot lower if the upstream ISP or the traffic sender is listening to the cost of the downstream ISP. By contractually stipulating a bound of the ratio, you very gently incent the sender to choose to be actually cognizant of downstream ISP's cost or the receiving ISP's cost. And this particular contractual clause is not very different from what I understand major ISPs do today with respect to traffic ratios, that the traffic I send to you over a pairing link and the traffic you send to me over a link should be within a factor of 2 or a 4. And it's a very similar clause, and it buys us, it keeps ISPs honest in this particular setting as well. So now extending this 2 ISP protocol to the multiple ISP case is straightforward. Consider this to be the internet and the destination, and it works very much like BGP in fact. So D here is the destination, G is the AS path, and C1 is the cost I'm talking about. So the green ISP here starts off BGP advertisement or BGP-like advertisements. What happens next is as soon as these are received into the networks, they are normalized based into units or into cost ranges that are meaningful internally to this orange ISP. While passing this cost on, it just adds on the normalized cost and its internal path cost. So C3 is basic, which is announced here to the blue ISP, is simply C1 dash, which comes from here, plus the internal path cost of this internal path. The blue ISP imports all these costs. It normalizes these costs again. Cost normalization is happening based on the pairwise relationship between ISPs, and it normalizes this. And one nice thing that happens through normalization, now you can compare C4 dash and C5 dash can be compared to each other because both of them have been normalized in the units that are meaningful to the blue ISP. This is something that you cannot do with MEDs today. That ISPs, MEDs, you cannot meaningfully compare MEDs received from two different neighbors. And these costs get to a particular source router and its path selection. It looks at that and picks a path that obeys this cost in particular. So it's operating very much like BGP. And here's how it performs. So these results are just simulation-based results over measured internet topologies. So these are not random graphs. These are internet topologies of ISPs that have been measured. And the left graph here is describing how much it might help you with over-provisioning. The black line is with BGP and the red is with Visor. And the experiment tried to say if there are some random perturbations in the network, such as link failures, the control that Visor provides you, how much it saves you in terms of provisioning the network. So what is showing, the difference here is showing, and the provisioning was measured relative to stable load. So what is showing, on average you have 8 to 10% provisioning advantage in this particular, with this set of topologies and experiment. So that's basically saying the Visor requires lower bandwidth provisioning, one of the original hypotheses I talked about. The right graph here is talking about path length. What it shows in the black line is again BGP, red is Visor. It shows the path length, how much higher the path length is relative to the shortest path in the network. So what it shows here is that while most of the paths are not longer, there's about 10% of the paths that are a lot longer with BGP, and now they are automatically shorter with Visor. No manual tuning required to fix even paths that were way long here. It's right here in the tail, like some paths were as long as 6 times the shortest path length. And these are not just short paths. Like I've seen like 20 milliseconds path being expanded to 100 milliseconds or so, just because of greedy path selection that happens. But Visor does a good job at fixing all of these paths automatically. So those are the benefits. At what cost do these benefits come? And to understand that, I have an implementation of Visor in Zorp, which is an open source router. And the implementation actually mirrors completely BGP, as you might have guessed from the Visor graphics slide I talked about. Less than 6% of lines of code were changed in the Zorp BGP implementation. And the extensions to BGP are very simple and backwards compatible. I simply embed cost in non-transitive BGP communities. You can also do that using optional non-transitive BGP attributes, and border routers jointly compute the normalization factors, and that computation is piggybacked on top of iBGP communication that is already happening between multiple border routers. And of course, the BGP decision process itself is slightly modified to take these costs into account. The other nice thing about Visor, it would benefit even the first two ISPs that use it. So you don't have to wait for all of the internet to deploy Visor. Even two ISPs that want to improve routing within themselves can start using Visor and see better path selection that happens. So here's a summary. I described Visor, a simple backwards compatible mechanism to coordinate interdomain routing between ISPs. And my hypothesis is this may lower provisioning, reduce the manual tuning that you need for egregiously bad cases, produces overall efficient paths, and may also help with interdomain QoS. And I'd repeat, like I'm basically here trying to understand whether or not these problems occur, and if anybody is interested in experimenting or evaluating with this. My email address is there for feedback and more details on how Visor works, and the prototype code is up there on the web. Thank you.
Ask two questions actually. Danny was here. First question is on normalization. How is it you actually do that with multiple ISPs? So you said you do normalization on a pairwise basis with each adjacent AS. How is it you actually normalize? What's that based upon?
So in this example and in the prototype implementation now, so both these ISPs, so think of it this way. Routing advertisements are going from both ISPs in either direction. So normalization happens based on the sum of the cost that you are announcing to me and the sum of the cost that I am announcing to you.
I'm saying, how do you derive the values for that? Though, just like with meds, right? For example, some people base it on propagation delay of a link times some factor link bandwidth or something like that.
Oh, I see. So in my experiments, I derived it based on what I was evaluating. In some cases, it was simply length of the link. In other cases, it was a combination of the metric. You could take in some other cases, it was basically a combination of utilization and latency is the short answer. And there were different exact weights could be placed on latency and utilization.
Right. Because traditionally, meds, for example, were derived, if you applied something intelligent to that based on, for example, the IGP metric to the next hop of the egress point of the network, something of that sort.
Yes, but those IGP metrics also have to be based on something like latency is what I mean. So the implementation actually uses IGP metrics, but given a topology, I also have to assign IGP metrics. Okay, so let me.
Randy, I think I can answer Danny's question. Whatever your metrics are, you're giving me a set of metrics across the links. I need to normalize them. I just normalize them by the sum of them. Who cares what they are? It's your business how you told me.
So I think when you have multiple...
Yeah, that's exactly right.
When you have multiple ASs, though, that would be an issue, right? I mean, unless... all right, I think I'll start this one. Okay, my other question, on slide 11, you had something, you said that there was 20 milliseconds in propagation delay savings or something like that. I was just wondering where that number came from. You said you had modeled control plane data, and then I was wondering where you observed 20 milliseconds data.
With those numbers, so these experiments are basically based on measured ISP topologies. 2 years ago, I had this project where I would go ahead and measure ISP topologies. And on top of the ISP topologies, what you can do is you can mimic BGP-like route selection. So these numbers are coming from that. What would happen if you were doing BGP-like default policy route selection where you prefer customers, peers, providers in that order, and compare that with the shortest path in the topology and the route and the path that would appear with visors. So these numbers are based on that.
So the topology there was both a control plane and a data plane.
So this is the length of the data path. So I don't understand the point about control plane.
We've read the rocket fuel papers. The point is, what would have happened if you'd taken hot potato? What would have been your path and what would have been the delay on that path? If you then use Wiser and Optimize, it will choose shorter paths. What's the savings on the shorter paths? And I believe what Ratul was saying, even though he hid the word, was he based it on the old rocket fuel data.
Yeah. Thanks, Randy. You're much better at answering the questions.
Now I have to remember my question. And I don't think I can. Oh, I remember it.
Yeah.
Yeah, vendors. This is cool stuff. Open your ears.
Oh, thank you.